Honors Pre-Calculus students, welcome to your 8.1 notes. Today is our introduction to matrices. We're going to do some row operations to solve systems. It's just a different way to do something we've already done before. Some of you have experience in this, some of you are rookies. So I think all of you will be able to catch up and get this figured out, but stick with me. Take good notes, write it down, bring it back to class with you, and you'll work in the room. So let's take a look at this. Let's start with some, it says reminders. For some of you that's true, for some of you this will be the first time. The first thing we want to talk about is the order of a matrix. You can see this first matrix here. This we call a 2 by 3. That's because it has 2 rows and 3 columns. 3 columns, 2 rows. So when we talk about the address of a matrix or of an entry in a matrix, we can find it based on the row and the column. The second matrix that you see here is a 3 by 1, 3 rows and exactly 1 column. All right, so that's how we talk dimension. It's always row by column. Matrices have multiple uses in the mathematical world. What we're going to focus on today is how we can use them to solve systems of equations. And you can see here a linear system like the variable 2 equation system that you see right here can be written in what's called an augmented matrix, where you have this extra row out here that's basically just your constants on the other side of the equation. And so you can see real easily how those two correspond and what you would do to write either a system into a matrix, or if you had a matrix, what that would look like if you wrote it as a system. Now, we've got a couple of forms that we'll talk about. Row echelon is the first one. The key to row echelon form, and this is, by the way, what we're going to be headed toward today, is that we have zeros right down here in this bottom left-hand corner. And then reduced row echelon form, this is an amazing way to work with matrices. It's a little more complex. We often let the calculator do this job for us, but you can see not only do we have these 3 zeros, but we also have zeros here. So what we're talking about is we have 1s in the main diagonal, which is right here. That's all 1s. Everything else is zeros except for this last column. And when you think about it, with this matrix that you see here, I'm going to erase some of my markings so we can actually see it again. This would correspond to this. It would just simply be x equals 3, y equals 2, z equals 1. Okay, so we will get to that point eventually. Today we're not going to quite get to the reduced row form, but we'll talk about what this looks like. So basically we have 4 operations we're looking at, and if we're being honest, it's really only 2 or 3. One of them is scalar multiplication. In other words, taking a row and multiplying by a constant. And we'll use that scalar multiplication on just about every step that we do with our row operations. The second thing is adding or subtracting rows. This is another one that we're going to do lots and lots of. Okay, the last 2, it says number 3, swap rows. That just basically means, switching 1 and 2 or 2 and 3 or whatever. We'll do that a little bit, but quite honestly, you don't really need that for the systems that we're working with. That's more if you're going to more advanced form like a reduced row echelon form, or just going to a modified echelon form is the way I would describe it. And then the last one is a combination. So really it's not a new thing. It's just basically you can do any 2 or 3 of those that are above all in one step. All right, so let's take a look at this. Let's go ahead and do a problem. The first one, you can see the system that's here. We're going to write this in matrix form. Our first row would be 5, -5, -5. Our second row is -2, -3, and 7. So we'll just go ahead and write that as a matrix. Now, our job to get this into our echelon form is we want to take this value right here that's currently a -2, and we want that to become a 0. Now here's the way I'm going to do it. I'm going to take 2 row 1s and I'm going to add 5 row 2s. So I'm going to rewrite that second row. We'll come back to the first row in a second. and I'm going to do 2 row 1s plus 5 row 2s. That's 10 minus 10, so that would be 0. That's what we're looking for right there. 2 row 1s would give us negative 10. 5 times negative 3 is negative 15, so that's giving us a negative 25. And then negative 10 plus 35 is, of course, 25. Now, the first row, we can rewrite it as is. Remember this whole scalar multiplication thing? If you want to make it look a little simpler, I'm noticing there it's 5s all the way around. I'd actually like to clean that row up and just make it 1/5 row 1 and make it 1, negative 1, negative 1. That step's not really essential, but it is helpful. And I guess you could look at the second row right now and say, hey, we could do 1/25 or negative 1/25 row 2 and clean that up even more, and that would be totally fine. I'm not going to mess with that though. What I'm going to do is this. I have a 0 here. That means I have a variable isolated. It's negative 25y is equal to 25. Quick division then tells me that y would be negative 1. Then I'm going to go back to this first equation, x minus y equals negative 1. And I'm going to plug in that value I found for y. That's x plus 1, so we subtract 1 from each side and we get x is negative 2. And we have our solution. It's negative 2, negative 1. Alright, so let's take a look at number 2. The first thing I'm going to do is write this as an augmented matrix. You'll notice that we have 3 variables this time, and we have to put in zeros any place we have a missing term, like right there, that's a 0x. And then on the last row, we're going to have a missing y value, so we plug in a 0 right there. Now, the key for us here is we have this little triangle in the bottom left-hand corner. We already have 1, 0, but the other two numbers are a 7 and a negative 5. And I need those 3 numbers to all be zeros. Folks, if you'll learn this pattern, you'll be able to solve these quickly and accurately every single time. I start right here with these 2 numbers, the 0 and the 7. Now, fortunately, the 0 is already a 0. I don't have to do anything there. So my job is to make that 7 become nothing. So on my next step, I'm going to rewrite row 1 exactly as it is. Because row 2 already has a 0, I'm not going to change anything. The only thing I am going to change is row 3. And I'll do that by taking 7 row 1s and subtracting 2 row 3s. 14 minus 14, that's going to give me a 0. Okay, I've skipped ahead just a bit here by filling out this matrix. The only row I changed was this third one, and again, it came from 7 row 1s minus 2 row 3s, so 14 minus 14. Negative 7 plus 10, 21 minus 0, and 7 times 24 minus 2 times 6. You can see all the values there. At this point, I really just have one more spot I have to work with. It's this number 3 right there. We need to change that to become a 0. So I'm going to leave row 1 the same. I'm going to leave row 2 the same. And here's the key, folks. When you change this number to a 0, don't try using row 1 and row 3. Although it would be easy to get a 0 here, you're going to lose the 0 that you have here. You'll undo what you did on the first step. You can get yourself into a painful, endless cycle of creating one 0 and losing another. So instead what we'll do is 3 row 2s, and we'll subtract 2 row 3s. You could do exactly the opposite of that. You'd get the same values. I'm going to skip ahead and fill out my matrix. Alright, you can see my finished matrix now. I've kept rows 1 and 2 the same. This third row came from taking 3 row 2s and subtracting 2 row 3, excuse me. And here's the key to all this, right here. This bottom row, 0, 0, negative 45, negative 270. There's an equation from that. Remember, this is x, this is y, this is z. This is on the other side of the equal sign. So what I know is that negative 45z is equal to negative 270. Some quick division tells me that z is equal to 6. We're going to use a process called back substitution now, where I'm going to take that value I found for z and go up one step, and I'm going to plug it in here. So 2y minus z, we're going to change z to 6, equals 14. If we add 6 and divide by 2, we quickly see that y would equal 10. Finally, I'm going to go back up one more step. I know that 2x minus y, 1y, which would be minus 10, plus 3z, well, that's 3 times 6, or 18, is equal to 24. So again, I found z, then I plugged in z here to find y. Now I'm plugging in z and y so I can find x, and I find when I subtract 8 and divide by 2, I get x equal to 8. So our ordered pair is 8, 6, and 10. Only lie that I told you was I just called that an ordered pair. That's clearly more than 2. That's an ordered triple. And now for our last one on the notes today. You notice right away this is kind of a weird problem. We have 4 variables in alphabetical order, x, y, z, w, of course, and only 2 equations. Folks, we're actually going to treat this very similar to what we have others. The only difference is we know this is an infinite solutions case, and we're going to have to solve in terms of other variables. Now previously what you've seen is that we've solved in terms of just one variable. We could put everything in terms of x, y, or z. Now in this case, because we are essentially 2 equations short of what we'd really need, we're going to have to actually solve in terms of 2 different variables, and I'll show you how that works. First thing I'm going to do, I'm going to kind of stick with the process before. I'm going to get a 0 right there in that bottom left hand corner. So I'm going to leave row 1 alone, and I'm going to change this to be 3 row 1s minus 4 row 2s. So our matrix looks like this. Now this is where it's a little interesting. Honestly, we're done with our work with the matrix on this particular problem. We're going to go back into equation mode, and I can see down here at the bottom I have an equation that looks like this. It's negative z plus 52w equals negative 54. I could choose to solve for everything in terms of w or z. I don't want to have 50 seconds as the fraction that I plug in to substitute back on the other equation though, so I'm going to solve for everything in terms of z. I'll get z is equal to 52w plus 54. So I know everything's going to be in terms of w, but I'm also going to have to pick one more variable, so we'll take a look at what that would look like. So I'm going to have 4x plus 12y minus 7, now this is z, so I'm going to plug in what I just found z to be, 52w plus 54 minus 20w equals 22. Alright, I've skipped ahead to the next step. I've gone ahead and distributed. And now what I'm going to do is solve for x. I honestly have the choice between x and y, what I want to solve for. I'd rather divide by 4 than divide by 12. There's really no reason other than that I'm choosing x. So I'll have 4x equals negative 12y plus 384w plus 400, and then I divide everything by 4 and I get negative 3y plus 96w plus 100. I know this problem's a little weird, but we're actually there. We've got our answer. It looks like this. Our x value is negative 3y plus 96w plus 100. So you notice we had 2 variables that we were working on there. Our y value is just simply y. That's one of the variables we're using. It's y and w. Our z value we found up here, 52w plus 54. And then finally, z is z. Folks, I know this is kind of a new concept for some of you, for others it's review. I hope you're picking up the basics. We'll get plenty of time to practice this in class next time we meet. Have a spectacular day.